Let me first hit roll. Answer your names, please. Bien. Here. Dilek. Here. In. Macho is here. Kramer. Up here. Karochinsky is here. Joshua Lopez. Brendan Lopez. Yeah. Yeah. I don't see the other one. Okay. Malberg is here. Martin is here. Reed. Retzlaff here. Richie. And Yakashenko here. All right. So if I recall, the last thing we did was chapter 7. And you guys were supposed to do the videos for chapter 8. Did we start chapter 8? Did we talk about,
we did start chapter 8, but we ended at part 3.
Oh, okay, yes, I do remember though. Thank you for reminding me. Right, so part 3 is where we ended, where we're dealing with percent composition and how do we determine the empirical formula. So what I'm going to do, just to get things rolling, is I'm going to do an example from the PowerPoint, which is basically what was covered in the videos, and then we'll look at particular questions. Okay. All right, so just to remind you, because we did see here. Hold on. Okay, let's talk about percent composition. I don't think we talked about that yet. Right, so when we're talking about the percent composition of a substance, we're talking about the percentage of mass of each element present in the formula of the substance. So for example, in the case of water, simple example here, if you're asked to determine the percentage, well, before I even go into that, so we know that the percentage of hydrogen in water is 11.19%, and the percentage of oxygen in water is 18.79%, right? And that is true for every sample of water. And we can calculate that very easily, because all we have to do is we get the molar mass of the compound if we know what the formula is, and then divide the total mass of each element by the molar mass and multiply by 100. And that will give you the percentage of each element present, right? So this is basically the simple formula that is used to determine the percentage of each element present in a particular substance. So for example, you're asked in this example to determine the percentage of percent composition of hydrogen sulfide. So the first thing you have to do is find the molar mass of hydrogen sulfide, and that would be equal to 2 times 1.008 grams per mole. That's for the hydrogen, and then you're going to add that to the molar mass of sulfur, which is 32.07 grams per mole. And we do the calculation, so that 2 times 1.008 plus, oops, 2 times 1.008 plus 32.07. And according to my calculations, this will be equal to 34.09 grams per mole. And therefore, to find the percentage of hydrogen, we take the total molar mass of hydrogen in the formula and divide it by the molar mass of everything, which is what we just calculated, times 100%. So 2 times 1.008 divided by 34.09 times 100. And according to my calculations, this works out to be equal to 5, how many sig figs? Okay, 4 sig figs, so 5.914. Right? And then we do a similar calculation for the sulfur. So sulfur is 32.07 grams per mole. And we divide that by the mass of everything times 100%. So that's 32.07 divided by 34.09 times 100. And this gives 94, 4 sig figs, 94.07%. And that's it. That's how you calculate the percentage of each element present, right? And one thing I always tell students to do whenever they're doing this type of calculation is that you can check to see if the answer is valid by adding these two together. It should be equal to, if not exactly 100%, close to 100%. So in this case here, if I add 5.914 plus 94.07, the answer I got when I add this up is 99.984%. So that's very close to 100, which means that the answers are valid. Not necessarily that they're correct, but they're valid, right? If you don't get 100% here or close to 100% here, then you know you made some error, and you'd have to go back and check and see where you made a mistake. All right. Okay. So that's as far as this is concerned. So, another way of determining the percentage by mass is based on experimental data. So let's say, for example, you're able to break down a substance into its constituent elements. You determine the mass of the compound that you start off with, and then you determine the mass of the elements in the compound, and you can determine the percentage in a similar way. So here's an example. I'm just going to go through this quickly. In this example, they gave you the mass. Hold on 1 minute. So in this example, they gave you the mass of the nitrogen and oxygen in a particular compound. And they're asking for the total, for the percent composition. So the total mass you need to calculate first. The total mass would be the sum of 1.52 grams and the 3.47 grams. And that would give you 1.52 plus 3.47, so 4.99 grams, right? And then now to determine the percentage of nitrogen, you take the mass of nitrogen, 1.52 grams, divided by the total, 4.99 grams, times 100%. So 1.52 divided by 4.99 times 100, and that gives you 30.6%. And then you do the same calculation, but this time for the oxygen, which would be 3.47 grams, divided by 4.99 grams, times 100%. So 3.47 divided by 4.99 times 100. And in this case, you're going to get 69.5%. And that's it. And again, you check to make sure that they add up to 100. 69.5 plus 34.6. And in this case, I got 100.1%, which is close to 100. So again, your values that you calculated, the percentages that you calculated will be valid. All right. So that's another way of determining the percent composition. Now, what is more challenging is if you are given the percentages upfront and you're asked to determine the formula for the compound. And there are two formulas that you can determine. One is the empirical formula that you can get directly first, and the other one is the molecular formula. So first we have to talk about the difference between the two. I think we covered this earlier, but it doesn't hurt for us to be reminded again. The empirical formula gives you the smallest whole number ratio between of the atoms of the different elements that is present in a compound, right? So if you're given something like C2H6, right? That is the molecular formula, right? The empirical formula for this compound would be CH3, right? Because this gives you the ratio of carbon to hydrogen atoms. The molecular formula gives you the actual number of atoms of each element per molecule, but the empirical formula gives you the simplest ratio of the atoms of the different elements present in the compound, right? Let me just skip all this here. These are just some examples of different compounds. Molecular formula and empirical formula. For example, in this case here, this is hydrogen peroxide. The molecular formula is H2O2. What that tells you is that for every molecule of the compound, there are 2 atoms of hydrogen, 2 atoms of oxygen. But the empirical formula is simply HO because it's a 1-to-1 ratio between the hydrogen and oxygen in that case. All right, and these are just some other examples. And what you'll find is that compounds having the same empirical formulas will have also the same percentages. And that is shown in these examples right here. CH2H2 and C6H6 are different compounds, but they have the same percentages because they have the same empirical formula. The ratio of carbon to hydrogen in each of those cases are the same. Okay, so let me get into an example of the reverse. If you're given a formula for a compound, if you're given the percentages for the compound, the percent composition, how would you determine the empirical formula? So the best way to learn this is to do an example or two. So here's one example, right? The question says, it gives you the percentages of different compounds or different elements in the compounds. Potassium, carbon, and oxygen. So these are the percentages. And the question is asking for you to calculate the empirical formula, right? So what I would do first is, and I like to do this in a tabular form. So I'm going to draw a table where at the top of the table, I'm going to write down the symbols of the elements. Potassium, carbon, and oxygen. Let me change the color of this thing because I hate red. Okay, so the first thing we're going to do is we're going to determine or write down the masses of each of these elements. Now, the question did not give us the mass of each element. The question gave us the percentages, right? So what we can do is that we can assume that we have 100 grams of the substance, right? If we assume that, that means that these percentages would represent the mass of each element present in 100 grams, right? So basically, in this row here, where I'm going to put the mass of each element, for the potassium, I'm going to put 56.58 grams. For the carbon, I'm going to put 8.68 grams. And for oxygen, I'm going to put 34.73 grams, all right? Then I will determine the moles of each of these elements. And by now, you all should be able to know how to do that. But just to remind you, you take the mass of each of them, 56.58 grams, and we multiply by, in the case of potassium, 1 mole over the molar mass of potassium, which is 39.10. So 39.10 grams. In the case of carbon, 8.68 grams. I'm going to multiply that by 1 mole over 12.01 grams. And in the case of oxygen, I'm going to multiply that by 1 mole over 16.00 grams, all right? So we need to work out each of these. So let me start off with the potassium, 56.58 divided by 39.10. So according to my calculations, this works out to be equal to 1.447 grams. I'm sorry, moles, because the grams will cancel out here and here. And then I'll do the calculation for the carbon, which is 8.68 divided by 12.01. And according to my calculations, this works out to be 0.727 moles. And then in the case of oxygen, 34.73 divided by 16. And according to my calculation, this works out to be equal to 2.171 moles, right? So that's how we get the moles for each of these masses. The next step is where we compare these numbers that we just calculated. And we decide which of these would be the lowest in value. And that obviously would be this one right here. So what we're going to do in the next line is divide all of them by the lowest value that we calculated, which is 0.7227 moles, right? So obviously when this divided by itself, that will give you 1, right? Now here we have to work out 1.447 moles divided by 0.7227 moles. So let's see what that gives. 1.447 divided by 0.7227. And according to my calculation, this works out to be equal to 2.002. And then over here, I'm going to divide 2.171 mole divided by the same, okay, so 2.171 divided by 0.7227, 0.7227 moles. And when I do that, I got 3.004, right? Now, obviously, 2.002 is approximately equal to 2 because we want to get the whole number integers at this point. And this will be approximately equal to 3, right? So basically, the ratio of the ratio of potassium to carbon to oxygen is 2 to 1 to 3, right? In terms of the moles. So therefore, these numbers will end up being the subscripts in the formula that we can determine, the empirical formula that we can determine for this compound. So therefore, the empirical formula for this compound would be K2CO3. And that's basically how we would answer a question like this. All right? Okay, any questions about this? Any questions you guys have? Including you guys out there in Zoom? Any questions? Okay, so if there are no questions, let me move on to the next slide. I think the next slide has another example, yes? Okay, so again, they gave us the percentages, and again, for a different compound, of course, and again, you're asked to determine the empirical formula, right? So same approach as before, but there, I think there's going to be a slight difference in how we're going to approach this closer to the end of this question. So again, I'm going to draw my table. I'm going to put nitrogen and oxygen at the top. And again, we're going to assume that we're working with 100 grams of the substance. So that means that these percentages can be expressed as the mass of different elements. So in the case of nitrogen, the mass will be 25.94 grams. And in the case of oxygen, that will be 74.06 grams, right? And then we find the moles like we did last time. So that would be moles. 25.94 grams. We're going to multiply that by 1 mole over 14.01 grams. And here, 74.06 grams multiplied by 1 mole over 16.00 grams, right? So let's do the number crunching here. Firstly, for the nitrogen, 25.94, divide that by 14.01. And according to my calculations, the answer when rounded off the 4 sig figs would be 1.852 moles. And then in the case of oxygen, 74.06 divided by 16, and according to my calculations, 4.629 moles, right? And then, just like we did the last time, at this stage, we compare these two numbers, and decide which one is the lowest or lower, because we told them of the lower value, and that would be this one, of course. So I'm going to divide both of them by 1.852 moles. And this would obviously give you 1. So let's do the same thing for this, 4.629 moles divided by 1.852 moles. And let's see what that gives. So 4.629 divided by 1.852. And here we have something interesting happening here, because when I did this calculation here, the answer I got is 2.499 when rounded off to 468. Now, 2.499 is not close to any integer, right? In fact, it's smack in the middle of 2.2 and 3, all right? So you cannot just simply round this off to the nearest integer, right? What you'd have to do in the next step, and that's the difference between this example and the previous one, is that you have to multiply these numbers by a certain integer to convert, especially this number, into an integer. So the question now becomes, what do you multiply through by? And the hint lies in the fact that this is approximately 2.5, right? And if you multiply anything 0.5 by 2, right, then that will be converted into an integer, right? So in this case here, we're going to multiply right through by 2, which means that this becomes 2, and 2 times 2.5 gives you what? 5, right? So therefore, now the empirical formula in this case is going to be equal to N2O5. So there are some instances where when you get to this stage, you cannot simply just round up or round down to the nearest integer. You have to figure out what number you multiply that number by so as to convert it into an integer, all right? Now, there are some numbers that you can easily tell just by looking at it. What do you round up by or round down by, or if you multiply by a number to convert it into an integer. I think there's a table which okay, so here is basically how you determine that, right? If you have a number which ends with 0.25, then that means that you multiply by 4 to convert that into an integer. If you have a number which ends with 0.333 recurring, right, then you multiply that number by 3. If you have a 0.666 recurring after the decimal point, you multiply that number by 3. If you have a 0.5, that means you multiply by 2. And if you have a 0.75, you multiply by 3. And there are some others as well, which is not included. For example, if you have a recurring, let me see if I can squeeze this here. If you have a recurring 1 after the decimal point, that means that you have to multiply by 9, right, to get to the nearest integer. And I think that's the only one I can think of right now. Otherwise, you'd have to do some trial and error stuff. You have to multiply by different numbers to see how you can convert that number into an integer. All right. Okay. So let me go to assignment number 8. No, that I didn't publish it, so let me do that now. Okay, assignment number 8. You guys have copies of assignment number 8? Okay. Yeah. And you guys out there in Zoom, you should be able to access assignment number 8. I'm going to scroll down to, oh, before we do that, there's one more thing I want to say. Let me go back to the PowerPoint. I'm sorry about this. What did I forget? So, remember I talked about the difference between empirical formula and molecular formula, right? So once you get the empirical formula, you can calculate the molecular formula, but you need an extra piece of information. And that extra piece of information will be the molar mass. And the way that helps you to calculate the molecular formula is by this equation right here, right? Let's scroll down to here. So basically, you need to calculate in some textbooks, they call this the integral factor, I, right? I is basically calculated by dividing the molar mass by the empirical formula mass, right? Once you get that I value, then you multiply that I value by the empirical formula, and that will give you the molecular formula. So let me give an example here. So here we have an empirical formula which is given already, and the question is asking for the molecular formula. So what we need to do is find out what the empirical formula mass is, and that would be equal to the sum of the molar masses according to the formula. So that's 12.01 grams per mole plus 2 times 1.008 grams per mole, right? So when we work that out, we do this here, 12.01 plus 2 times 1.008, and according to my calculations, this works out to be equal to 14.03 grams per mole, right? So to find I, that would be equal to the molar mass, which is given here, 126.2 grams per mole, divided by 14.03 grams per mole. And let's see what that gives. Oh, wait a minute. Did I do something wrong? Okay, no. Okay, so 126.2 divided by 14.03. And according to my calculation, this works out to be equal to 8.995, which is approximately 9, right? So therefore, the molecular formula would be equal to the empirical formula, which is CH2 multiplied by 9. So that works out to be C9H18. And that's how you get the molecular formula from the empirical formula. And that's how that is done, right? So that's very important for you to know because of the questions that you'll be looking at in this assignment. So let me go to the assignment. And the question that we're going to look at here together, based on this topic, is not this question. This question, okay. So, part 3, number 1. This question says, determine the molecular formula of each of the following compounds. So, based on what we have just covered so far, right? How would you do A? In the case of A, they gave us the empirical formula and they gave us the molar mass. All right, so I want to hear what you guys have to say, especially you guys out there in Zoom. I want you to chime in. What would be the first step in this process? They gave you the molar mass, and they gave you the empirical formula in this case. So what would be the first step in this process? For the example that we just did in the PowerPoint. The last example. Huh? Stable. Oh, no. That would be for B. Right. The very last example that we did, the one dealing with the empirical formula, or dealing with getting the molecular formula from the empirical formula. The very last example. Okay, So in other words, you calculate empirical mass, right? So that would be 1.008 grams per mole plus 12.01 grams per mole plus 2 times 16.00 grams per mole. Of course, those numbers you'll get from the periodic table. So 32 plus 12.01 plus 1.008. So according to my calculations, excuse me, that gives 45.02. 45.02 grams per mole. Okay, very good. Next step. After we get the empirical mass, what's the next step?
Don't we divide the molar mass by the empirical mass?
Good. So that would give us the integral factor. So 90.0. By the way, who said that?
Stephanie.
Okay, very good. So yes, you're absolutely right. You divide the molar mass by the 45.0, whoops. 45.02 grams per mole, right? And when I do that on my calculator, I got basically rounded up to 3 sig figs. So that will be 2.00, which is equal to 2. So what's the next step? Now that we have I, how do we use that to determine the molecular formula?
You would multiply the elements of the empirical formula times 2.
Good. Multiply all of this by 2. So the final answer is H2C2O4. That's the final answer. All right. Okay, very good. Any questions about this one? Any questions? Any questions? Any questions? Any questions on their Zoom? Okay. Is it okay for me to clear this? All right, let me clear this. And let me scroll down to the B part. Now the B part is where you were asking about the table. That's where the B part comes in, right? So in the case of the B part, they gave you the percentages of each element present in this compound by mass. They also gave you the molar mass, right? And the question is asking for you to, again, determine the molecular formula. So in this particular case, what you have to do is determine the empirical formula first, based on the data provided. So let me construct my table here. So carbon, hydrogen, and oxygen are the 3 elements present. Right? And as I said before, what we do is that we assume that we're working with 100 grams, which means that these percentage values will represent the masses of each element. So for carbon, that is 75.69 grams. For hydrogen, that is 8.80 grams. And for oxygen, that is 15.51 grams. Okay, so I'm getting you off to a start here. So I need you guys to tell me what would be the next step in this process. What's the next step? What would be the next line? Let me ask you that. And feel free to follow the example that we did earlier.
Is that the mole?
Okay, moles. So how do we calculate moles for the carbon? What do we calculate the moles for carbon? What did you do in the example that I worked earlier? 75.69 grams, what do we multiply that by? Over 12.81, very good, right? And what about the hydrogen? What do we multiply that by? 1 mole over? Okay, very good. And then in the case of oxygen, 15.51 grams multiplied by what? 1 mole over 16.00 grams. Okay, remember those numbers you obtained from the periodic table. All right, so let's do the number crunching. 75.69 divided by 12.01. And according to my calculation, this works out to be equal to 6.302 moles. In the case of hydrogen, 8.80 divided by 1.008. And according to my calculation, this works out to be equal to 8.73 moles. And then in the case of oxygen, it's 15.51 divided by 16.00. And according to my calculation, this works out to be equal to 0.96, so 0.9694. All right. And that's how we get the mole, right? Okay, what's the next step? Now that we have the moles, the next step is what? Exactly. So the smallest number is that right there, right? So we're going to divide right through by 0.9694 moles. So that is 6.302 moles divided by 0.9694 moles. Here we're going to divide 8.73 moles by 0.9694 moles. And this divided by itself will give you 1, all right? So 6.302 divided by 0.9694. So according to my calculation, this would be equal to 6.500. And then 8.73 divided by 0.9694. And that is going to give you, according to my calculations, 9.01. All right. Okay. So at this stage, what would be your next step? Exactly. Multiply everything by 2. Now I've run out of space here. Let me just continue up here. Multiply by 2, right? So the 6.5 for carbon, when you multiply by 2, that will give you 13. And the for the hydrogen, that will give you 18.02, which is approximately 18. And for the oxygen, when you multiply by 2, you're going to get 2 here. So these would be the subscripts in the final answer. So let me squeeze the final answer here. So the final answer for the empirical, well, actually, not the final answer, that's the empirical formula. The question is asking for the molecular formula. So we're not quite there yet. So the empirical formula is equal to C13H18O2, right? So that's the empirical formula, but we're not finished yet because the question is asking for the molecular formula. So now that we have the empirical formula, how do we get the molecular formula? And here's the hint right here. They gave you the molar mass, right? So we have the empirical formula. They gave you the molar mass. So how do we get from the empirical formula to the molecular formula? What did we do in the last question? With the empirical formula in the last question?
You divided the molecular mass by the empirical mass.
Okay, very good. So the to get I, right? The molar mass divided by the empirical mass, right? They gave us the molar mass already, right? The empirical mass you get by adding up all these. Okay, so I'm just going to do a quick calculation of that here. Carbon is 12.01 times 13 for the carbon plus for hydrogen 1.008 times 18 for the hydrogen plus 16 for the oxygen times 2. And guess what? The molar mass is equal to, rounded off to 2 decimal places, 206.27 grams per mole. No, I'm sorry, my mistake. The molar mass is given as 206 grams per mole, and the empirical mass is 206.27 grams per mole. So guess what? I is equal to 1. So what does that mean? It means that the molecular formula is what?
The same as the empirical formula.
C13H18O2, right? So if I is equal to 1, the empirical formula and the molecular formula are both the same. All right? So that's basically how you do B. Okay? Any questions about this? Any questions? Any questions? Any questions out there in Zoom? Okay. Is it okay for me to clear all this? Okay, so let me see what's the next question. All right, let's look at number 2. What time is it now? Oh, we have it. All right, let's look at number 2. Number 2 is asking for the empirical formula, and it gives you the masses of iron, sulfur, and oxygen. So how do you think you go about solving this one? Well,
Would you
oh, I'm sorry, go ahead.
you would add up all the grams and then divide it by each one?
Oh, okay, you could do that. But that would be a longer route, let's put it that way. I mean, there's nothing wrong with that, going that route, but it's not necessary, let's put it that way. What you could do instead is that you could just simply use these masses in the first line of the table, and then you do the same thing as we did before. So let me just start you guys off. It contains iron, sulfur, and oxygen, right? So since they gave you the masses already, all you have to do is write down those numbers under each of these, right? So in the case of iron, that would be 0.0134 grams, 0.00769 grams, And then for oxygen, that would be 0.0115 grams, all right? So next step. Find the moles. So how do we do that in each case? Let's start off with the iron, 0.0134 grams. We multiply by what? 1 mole over the molar mass of iron, which is 55.85 grams. .85 grams, all right? And then in the case of sulfur, you do the same thing, 0.00769 grams. Excuse me, multiplied by 1 mole over the molar mass of sulfur, which is 32.06 or 7, don't remember. 7. And then in the case of oxygen, it's 0.0115 grams multiplied by 1 mole over 16.00 grams. And let's see here what will result from this. So 0.0134 divided by 55.85. And according to my calculation, this works out to be equal to 2.36. So that will be 2.40 multiplied by 10 to the minus 4 moles. And then in the case of sulfur, it would be 0.00769 divided by 32.07. And according to my calculation, this works out to be equal to 2.6. Okay, 2.40 again. Times 10 to the minus 4 moles. By the way, I should have the mole unit here as well. And then in the case of oxygen, it's 0.0115 divided by 16. And the answer I got here is 7.19 times 10 to the minus 4. And again, folks, please check to make sure I'm doing the right thing, because of course I'm only human and I can make errors. So do these calculations along with me so that you keep me on my toes, all right? But these are the answers I got for calculating the moles of each element present. So what's the next step? Now that we have the moles, the next step would be what? Exactly. So you divide right through by 2.40 times 10 to the minus 4. This will give you 1. This will give you 1. And in the case of oxygen, let me do that calculation here. Moles. Moles divided by 2.40 times 10 to the minus 4 moles. Let's see what that gives. 7.19 times 10 to the minus 4 divided by 2.4 times 10 to the minus 4. So according to my calculations, rounded off to 3 sig figs, that's going to be 3.00, which is going to be equal to 3. So therefore, the empirical formula for this compound is SO3. And that would be how you do that. That's how you do that. All right. Okay, any questions about this one? Any questions out there in Zoom? Any questions out there in Zoom? Okay, can I clear this? Let's scroll down to see what is further down. Okay, so what I'm going to do is I'm going to direct you to do the other questions. Let me just look at them. So you should be able to do number 3. You should be able to do number 4. Number 5. And that's it, right? So the rest of this assignment you should be able to do. So what I'm gonna do now is open up a Dropbox for this. This is assignment number 8. So let me. Today is the 25th. Okay, too far ahead. Okay, today's the 25th. I'm going to let it be due by Friday, right? Let me just do some other things here, just to make sure. Okay, so that's the due date, and it's going to be available from now. Let me publish it, of course. Let's check something here. Okay, so it's now available, the Dropbox that is. It's now available for you to submit an assignment. So that will be due on Friday. Make sure that it's in a PDF format. All right. And that's pretty much it. Before you guys leave, I'm sure you saw the announcement I made today about the test that you guys should have done before the break. I don't know what happened, but a lot of you did not do the test. So if you want to do the test, please contact me so we can make arrangements, so you can make up that test. I would think that you would want to do that test because there's only 3 tests given and I'll be dropping the lowest score, all right? So make sure you contact me. You can call me or Skype me during my office hours so we can make arrangements for you to do that particular test, all right? Test number 2. All right. And I think that's all I have. Oh, and also make sure that you watch the videos for chapters 9. Well, let me see here. I'm going to post this announcement online as well. Chapter 9. Okay, chapter 9, very important. So let me go to the modules section. Where's modules? Modules, very okay, modules. And then chapter 9. Okay, so that's chapter 9 right there. Make sure that you watch those videos, all right? And come prepared to discuss chapter 9. We'll be doing problems just like we did today, which involves the topic covered in chapter 9. Chapter 9 covers a very important topic in chemistry known as stoichiometry, which is very important, a very important skill for you to master. So it's very important. Make sure you watch the videos, follow the examples, and come prepared next class to have a discussion, all right? Okay, so that's pretty much it for today. So I'll see you guys next Tuesday, all right? So for you guys out there in Zoom, I'm going to sign off now.